Hello everyone. So in this pre-lecture tutorial, we're going to connect a couple of concepts together. We're going to join what we've learned with the gas laws in this chapter with what we learned about reaction stoichiometry a couple of chapters ago. So on the screen right now, I have a problem that we can use to sort of walk through this process. And if we read through the problem, they're asking for me to calculate a volume of hydrogen gas, okay, at conditions that are STP, we'll discuss that again in a moment, which is being produced from 6.54 grams of zinc when it reacts with hydrochloric acid. And so again, I brought up this notion of STP, or standard temperature and pressure, before. Basically, standard temperature is 273 Kelvin, and standard pressure would be 1 atmosphere. Now, notice that I have the temperature of this hydrogen gas, I have the pressure, and if I use the 6.54 grams of zinc as a starting point, I have the means by which I can calculate the number of moles of hydrogen. So seeing these variables lined up this way, it should bring to mind the ideal gas law. Okay, PV is equal to nRT. And I'm being asked to solve for a volume of hydrogen gas. And so what that means is if I solve for V, once I find the number of moles of hydrogen, I can go ahead and plug into here and find the volume of hydrogen that's involved in this particular reaction. And so basically, I would begin from the 6.54 grams of zinc. And again, when it comes to stoichiometry, again, the goal is to convert to moles so that you then can use the mole ratio from the balanced chemical equation to finish solving the problem. So I'm going to convert these grams of zinc to moles of zinc. And if I consult the periodic table, basically there are 65.41 grams of zinc in 1 mole of zinc. All right, now I'm in units of moles, and I would have to convert those moles of zinc to moles of hydrogen gas. And so if I consult the balanced chemical equation, I see that each of those coefficients is 1, so that means I have a 1 to 1 mole ratio. So I would then just simply do the math. If I take 6.54 and divide that by 65.41, if I then multiply that through by a mole ratio of 1, I get 0.0998. Oops, sorry, there was one more 9 in there. 0.0998 moles of hydrogen gas. Now, I'm not done with the problem because they asked for the volume of the hydrogen gas, and so I'd have to take this number of moles of hydrogen and plug it into the ideal gas law. And so I would go and carry through the 0.09998 moles of hydrogen. Okay, R is the ideal gas constant, 0.0821 liter atmospheres per mole Kelvin. The temperature is, again, standard temperature, so that's 273 Kelvin, and the pressure is 1 atmosphere. So if I look at my units, the moles would cancel, the Kelvin would cancel, the atmospheres would cancel, and I'm left with an answer in liters, as I should. And so if I go ahead and do that math, take the 0.09998, multiply it by 0.0821 times 273, basically I get 2.24 liters of hydrogen gas. And so I could solve the problem this way, but believe it or not, there's a bit of a shortcut, all right? And I wanted to make sure that you guys were aware of this particular concept, Okay, we're actually going to demonstrate how to calculate the molar volume of a gas. So what that means is I'm trying to calculate what volume in liters a gas would occupy if I have 1 mole of the gas at standard temperature and pressure. So at STP, which again we know that the temperature is 273 Kelvin. I know that the pressure should then be 1 atmosphere. So if I'm solving for this volume, again, V is equal to nRT over P. And so if I plug in, that's 1 mole times the ideal gas constant, 0.0821 liter atmospheres per mole Kelvin. The temperature was 273 Kelvin, and the pressure is 1 atmosphere. So if I go ahead and do that math, so that's 1 times 0.0821 times 273 divided by 1 atmosphere, and I get a volume of 22.4 liters. So what this is telling us is that all gases occupy 22.4 liters if I have 1 mole of the gas at STP. And so I'm sure you're looking at this result and saying, well, big deal, right? But as it turns out, it actually makes solving this type of problem super easy, because basically what I can do, all right, and I'll actually change colors so you can see how you would solve this problem using the molar volume of a gas. I would start it as normal. Okay, so it would be 6.54 grams of zinc. Okay, and I'm going to divide by the molar mass, 65.41 grams of zinc for every 1 mole of zinc. But rather than explicitly solving for a number of moles of hydrogen and taking that into the ideal gas law, instead, I can use one simple conversion factor in this next part of my dimensional analysis and be done with the problem in one swing. So basically, based on this result for the molar volume of a gas, where there are 22.4 liters per 1 mole of gas, that means I can use that here. I can say for every well, first I have to apply the mole ratio. Basically, I have 1 mole of zinc for every 1 mole of hydrogen. All right, but then from here, I'm going to go ahead and say that for every 1 mole of hydrogen, since I'm at STP, that hydrogen should occupy 22.4 liters. So this shorter dimensional analysis setup will actually get the problem solved just the same. I would have 6.54 divided by 65.41 times 22.4, and I still come up with 2.24 liters with just a little bit less work. And so go ahead and respond to the question attached to this pre-lecture tutorial video. Practice using these principles of gas stoichiometry, and then we'll move on from there in chapter 11. As always, if there are any questions, feel free to email me, or if you'd like, you can leave a comment on Google Classroom. Okay, so have a good night. Stay safe.